iMac because it is provided by Unum. I can update only my
Mm,
yes.
okay.
So just take this book LC once and the beginning. You don't need to worry about the beginning chapters. You can follow the book which I have shared with you, that Mac Owen. And if you have taken a look on this book, then this is really in a simple language. So for the basic thing, you can go for that. But after reading this, you can read this book because the best the best way to understand anything is to read all the books and go through the stuffs which is provided in the books that cannot be provided by anything. So when you study a topic, when I am teaching a topic in the class, I would suggest that just go for the book. It is my strong recommendation. Even I do that. So this notes is basically followed by LC Vaughan's book. Actually, for my interviews, I have read the book by L.C. Mons, so that's why for me it is easier a little bit. Yeah, so page number which I have uploaded in your Google Classroom, there are something missing in page number. Like I downloaded it with using Library Genesis, and there is something bad. So the page number 567, that is the starting of chapter. However, in the content, it is showing that it is page number 8 something or 6 something. So that's why I just write the page number. So the conservation law. Suppose this is a domain omega, and this is the boundary of the domain del omega. So the domain is this region where the variables are defined. This is the region of our interest. So consider a domain omega. Consider a domain omega contained in Rn. Okay. When we talk about the domain, so always keep in your mind that domain is an open set in Rn. Domain is an open set in Rn. I am not going to tell these things every time because we are going to define the derivative in the domain. It means we are not considering the boundary. Okay, so consider a domain omega contained in Rn and a quantity of interest capital U. So this capital U is a vector function here. It will be U1, U2, comma dot 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 U1 R say UK. So and a quantity of interest U defined for all points x belongs to this omega. The quantity of interest U may be temperature of the rod, the pressure of a fluid, the concentration of a chemical which we drops on the surface of a river, the river and the group of cells, and the velocity of the blood cells in the cardiovasculars, and conservation of mass of a fluid, momentum of a fluid, energy of a fluid. It can be any quantity of our interest, the quantity of our interest in which we want to see the change with respect to time, evolution in that quantity. Evolution, when we talk about the evolution here in partial differential equation, the evolution is taken the change with respect to time. So the quantity of interest U may be the temperature of a rod, the pressure of a fluid, the pressure of a fluid, momentum of a fluid, fluid, concentration of a chemical, and to name a few. Like I am just telling you a very small name here, but it is a number of quantity because we are going to talk about the oceanographic phenomena, the atmospheric phenomena, the aerodynamics phenomena, like the when the airplane fly, so the wings of the airplanes create some disturbance in the surrounding. So what happens? The wings, when the airplane flies, so what it wings done, what it creates some disturbance, and the velocity of that disturbance is greater than the velocity of the surroundings, like the velocity of the sound. So there the shock wave arises. So in aerodynamics, astronautics, oceanography, mathematics, biology, engineering, this conservation law is formed in each of the branches of these sciences. And this quantity of interest can be anything, like the velocity of the fluid, the pressure of the fluid, mass of the fluid, momentum, concentration of the chemicals, heat flow in a rod. So the evolution, and when I'm talking about the evolution, so basically it is increase or decrease in this quantity of interest, and that is taken with respect to time, evolution in time. So the evolution of this quantity of interest u can be described by a simple phenomenological observation. So here I am writing the definition of the valence law or conservation law. So the temporal rate of change, the temporal the temporal rate of change means change in this quantity of interest with respect to time. Change in this quantity of interest with respect to time. So the temporal rate of change of u in any fixed domain omega is equal to the total amount of capital U produced or destroyed inside omega, and the flux of U across the boundary del omega. I would like to be careful with this omega, because omega is the time, and okay, so he's talking, yeah. So this omega is contained in Rn, because we are only talking about the rate of change of U. So the quantity U will be defined in omega cross R plus, because this is containing only the variable x. However, U is also changing with respect to time, so U will contain in this. So the temporal rate of change of U in any fixed domain omega is equal to the total amount of U produced or destroyed. If amount U is produced inside this domain omega, then it works like a source. Something is produced. or destroyed. So if it's something sink here or something destroyed here, so it works like a sink inside omega, and the flux of u across the boundary delta omega. So basically, what is the term flux? Can anyone tell me what is the term flux?
It's the volume per unit time.
Sorry.
The volume per unit time.
I'm not talking about the mathematical terms. I am talking about its physics. What you understand with this flux?
Flux is the given volume that it's passing through a certain area.
Yeah. So flux is like it is.
The integral.
I will not go for the integral now. In just if you will look at this, so something is coming and something is going, like at the boundary of the at the boundary of this domain there is some magnitude, and which is also representing the direction of the flow. So basically, what is the meaning of flux? That is a magnitude that is passing or crossing this surface, that is passing through this boundary. It is not defined inside the domain. It is defined at the boundary of the domain. So if some part of the fluid is crossing this boundary, so the you can say basically volume. So the magnitude of that volume which pass through this surface, so it has some direction. If it is entering, if it is going outside, so it denotes unit normal. So its magnitude, why I am saying its magnitude, because we are going to take this thing in effect. If it is going outside, then we will take negative sign. If it is coming inside, then we will take positive sign. So a volume which will pass through this surface, either coming inside or going outside, so that is known as flux. Is it clear? So so boundary del omega, that is the change in u. Now here I am defining that the temporal rate of change of u in any fixed domain omega is equal to the total amount of u produced or destroyed inside omega, and the flux of u across the boundary. Flux is defined on the boundary because we are talking about the volume, that the magnitude of that volume which passed the boundary, which is defined on the surface. It is not inside. So in change in U is because of two quantity. The quantity of U which is produced or destroyed, that we treat as a source term, and the flux of U across the boundary, that is the flux. So the change in U is due to two terms, is due to two factors. I am telling just what is coming in my mind, but I have written a better definition in your notes. The source or sink. Sink means something is sinking, something is destroyed. Source means something is emerging, something is created. Source or sink representing the quantity produced or destroyed, and the flux and the flux represent.
Right now, I'm remembering that uh, at a colloquium right here, uh, 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 and in a PhD professor was invited to give a talk about uh, dissipative swell propagation across the Pacific.
Mm-hmm.
And all of this, like PDE, formalism, uh, I saw how he applied like conservation laws in
Mm-hmm.
the, I don't know, maybe, I remember something about like the ocean does not lose mass. So there's an equation for that, or the Laplace equation for conservation, or for the sinks and the sources of energy. So I just want to point it out because he mentioned like a lot of conservation laws.
Yeah, so conservation law, basically this is my research area which I am working. So if you will open your notes in your laptop. So here I am also going to give you some example and I would like to ask you to work on this example. Like transport equation, we already have studied the P system and the Euler's equation of gas dynamics. I will give you the shallow water equation here as well. I am going to give you the traffic flow problem and
He also said said that the swell propagation across the Pacific was a lot easier than shallow waters.
which propagation.
The dissipative swell propagation.
Okay, yeah, shallow water is a little bit difficult, and I
Yeah,
will
he
tell
said that shallow water was more difficult.
yeah, but
Mm.
I am not going to tell you the difficult one. Actually, currently I am working on two-layer shallow water flow, so that is my research area, and I do the model formulation and then I work like everything. So I'm not going to present a very difficult shallow water model formulation because if we are considering all the effects from the oceanography in any kind of model formulation, then it is just going to increase our difficulty. But here I am not going to make you scared. My aim is just to tell you what is the conservation law and how the real life phenomena is formed and how it is hyperbolic. When you will be doing the research, then for sure you are going to go through the higher, like the difficult problem, the peculiar behavior of that shallow water flow, which I am working. But for the time being, we should have the idea of what is the Euler's equation of gas dynamics because we are not restricted only till the Euler equation of gas dynamics. A lot of author has worked in the past, but since this gas dynamics or this basically fluid dynamics, say because gas and liquid I am considering on. So this fluid dynamics is very emerging area in the real life application. So we will not be restricted to only Euler's equation of gas dynamics. We are not compelled to do only these things. We can do anything. I can suggest you books as well. But here I would present you very simple model and we will do very simple calculation and the correct method of characteristic to find out the solution, rarefaction, problem, shock wave. So we will do a simpler thing. However, I can also give you some books and some references to even you can read a paper. I can give you a paper and the papers are really good. But we will go. Firstly, we need.
Actually, I, I was thinking about like I know that there's like a Schrodinger equation for like flows of water. Like I don't know if there exists like a,
When
I
you
don't
talk
know.
about Schrodinger
Yeah,
equation,
yeah, yeah. That like bothers me a lot because I'm a physicist and there's the Schrodinger equation from the like the quantum.
yeah, I am not going to discuss the Schrodinger equation because what I know that in the Schrodinger equation there are imaginary terms considered like iota or something. So I don't go over that like Schrodinger equations and these kind of things. I work on very realistic phenomena. You can analyze those things. So till the date I have worked on the black hole theory. Like my PhD work was on the gaseous phenomena in black hole theory. So I switched to the liquid flow like shallow water flow. Currently I am working. So I am working on the more realistic phenomena, not on the Schrodinger. I work on the extension of the Euler equation, and currently I am doing the model formulation by considering the Navier-Stokes equation. In the Navier-Stokes equation, I take the viscous terms zero and then take the averaging process, because as I was discussing, when we are in the ocean, the horizontal length is much higher than the depth of the ocean, because if you are standing on the shore of an ocean, so we can see that it is spread, even we cannot reach there, but its depth is not that much. Like scuba diving, most of the people do scuba diving, they go on the depth of the ocean, but the horizontal length is much higher than the depth. So we do the averaging process to make it more realistic in the averaging process of the Navier-Stokes equation. So how I formulate the model. So the situation mathematically expressed as I will tell you what is the meaning of these things. Just hold on. So this quantity in which we are taking the temporal rate of change, this basically represents the total amount of the quantity within u at any time t, within omega. So what was our, let me copy this uh, figure so that I can paste there. So this was the figure which I was taking. So just take a notes. So if this is any smooth bounded domain, say omega, which is contained in R, and this integral omega u dx represents the total amount of this quantity within omega at time t. Okay, so if we take integration in two dimension, you already know this, just you need to memorize your things. So if this is x, this is t, and we are taking the integration between a to b. So what does this integration represents? The area which is swept below this line, that is your integration. What is the meaning of integration? It represents this area. So the same thing is happening. This integration in this domain omega represents the total amount of this quantity, because it is measuring the quantity which is in this omega, inside the omega of this quantity within this domain at any time t. So this you already know, so that was not a big deal. Nu is unit outward normal, and d sigma x is the surface measure, and f is the flux, and s is the source term. So F is the flux, nu is the unit outward normal, and d sigma is the surface measure. So it represents the basically the volume which is crossing the boundary and which is coming inside the boundary. This whole integration, because again we are taking the integration on the boundary, so it is going to represent the quantity which is crossing and which is coming inside the boundary. And if we are going to measure the quantity u that is destroyed, or that is destroyed or created inside omega, again we need to put this integration, because we are measuring that quantity. So I am calling it S, that is either it may be source or it may be sink. Now, for this term, we use the Green's Gauss divergence theorem because that is on the surface. Um, so you can write it. It is flux and it is source. So the minus sign in front of the flux term is for convenience. Why I am saying the minus sign for the convenience? Because here I am saying that the quantity is going outside. The quantity is going outside because you know that if we are giving heat to a rod and the rod is most of the time the rod is not insulated, so it will pass their heat outside of the boundary. Is not it, it will pass some heat outside of the boundary. So we assume here, just for the convenience, that that volume is going outside through the boundary, because every time we cannot take an insulated rod. So that is the negative sign. If there is something that is coming inside the boundary, like suppose you have you have a cold water in a steel glass, then what will happen? The temperature outside that steel glass will go inside that glass. The temperature outside will go inside, and the water will start to be in the resemblance of the room temperature, like it start normal temperature. There, the heat is the heat of that water is coming outside with the boundary of the glass. So the same thing. So it is taken to be negative just for the convenience, and we can change accordingly of our real life simulation, according to our real life simulation. So using the Gauss divergence theorem, using the Gauss divergence theorem, and firstly, let's use the Gauss divergence theorem and then we will use the fundamental theorem of calculus. So when we use the Gauss divergence theorem, it becomes d over dt integration u dx plus omega. I just passed it to the left side. This surface will change to the divergence of f, and this f is function of f dx is equals to integration omega s dx. Now we will use the fundamental theorem of calculus for the first term, fundamental theorem of the calculus. So if we are taking the derivative with respect to time, it will pass inside this del u over del t dx, and the derivative will apply on the lower limit and on the upper limit. So we are assuming that the boundary is fixed, so the derivative of constant quantity is going to be zero. What fundamental theorem of calculus says?
Isn't the Barrow rule or something like that?
Sorry?
The Barrow rule.
Not it. Its name is fundamental theorem of calculus. I don't know how we are calling the value. So when the derivative is applying the outside of, so this go inside ax bx fx dx. Say it is x, d over dx fx dx. Then come to the upper limit plus the value of f x at x equals to b db over dx minus the value of fx at x equals to a and dA over ds. Now we are taking a fixed domain. We are taking a fixed domain. So the lower limit and the upper limit will be some fixed quantity. As soon as b and a becomes constant, this will vanish. And we are left with this term. So using the fundamental theorem of calculus, this derivative will come inside of this, and I am taking the partial derivative because now u is also function of x. Now we have taken any arbitrary domain omega, so if we keep it like this, this integral is 0 and this omega is an arbitrary domain and the integral of a quantity is 0, so the quantity will be 0. Sorry, this is plus. Zero r you can write is equals to s. So this source is also function of u. I am not mentioning here because the quantity u that is destroyed or created inside omega, so it is going to be a function of u. Or in the notation form, we can also express it is just a way. And now you will see that u is belonging to omega cross r plus. U is function of x and t. And where is omega contained? It is contained in Rn cross r plus. Is not it? And to solve, this is your balance law. To solve this, we also define an initial or boundary condition. So here I am going to give you the initial condition, that is at p equals to 0. So u at x comma 0 is u naught x. And that is defined on u naught is belonging to omega cross 0. That is contained in Rn cross 0. This domain is very important, so always keep in mind how I am defining the domain. Say this is your equation number 3. I am writing the equation number 3 because I have written in your notes. So I don't think I need to mention here. So the differential equation 3rd is often termed as Balanced law. Balanced law. Why we call it Balanced law? As it is a statement of the fact that the rate of change of u is a balance of the flux and the source. Is a balance of the flux and the source. If both quantity were the derivative of some function, then it was conservation law. But there is some term that is known as source term. This quantity is balanced by a non-derivative term. This quantity is balanced by a non-derivative term. So that's why it is called a balanced law. If this source term, there is no quantity, there is this quantity of interest u is not creating or destroying inside the omega, that is the source is 0. In that case, it will reduce to this form, f of u equals to 0. And here the temporal rate of change of u is only measured by the flux of u across the boundary. So it is called your conservation law. Conservation law. So this is a very thin line difference between the conservation law and balance law, and most of the time people call it that it is a conservation law most of the time, but now you know, so be careful when you are calling it a balance law or when you are calling it a conservation law. So this equation is known as conservation law, as the only change in u comes from the quantity entering or leaving the domain of interest. Now I am giving you an equation and just solve it. Using the method of characteristic, assuming that n is smooth. N belongs to omega cross r plus, and that is contained in r comma r plus. Just solve it using the method of characteristic. You always know the method of characteristic. You already know because I have already explained you. So use the method of characteristic and solve it. Just give me 5 to 6 minutes. I am coming back. Please solve it.